Welcome to this presentation in the series Electronics, the Story of One Human Lifetime, presented by David Beams and Gary James. I am David Beams. I will be your narrator this evening. I am an Associate Professor Emeritus of Electrical Engineering, and the subject of this video is using the One Human Lifetime Project resources to design a Chebyshev low-pass filter. Our questions for this presentation are: how does a Chebyshev response differ from a Butterworth response? How do we use the One Human Lifetime Project resources to design a Chebyshev low-pass filter? And how do we simulate the filter with LTSpice and verify its performance? So let's take up the first question. Here I have a comparison of the frequency response of a Butterworth fourth-order low-pass filter and a fourth-order Chebyshev low-pass filter. The Butterworth response is this yellow curve, and you notice that at low frequencies, the gain is absolutely flat, 0 decibels, and then it rolls off smoothly and it makes its transition toward the stop band. Okay, but now this white curve, that is the Chebyshev low-pass filter. Now, the Chebyshev filter and the Butterworth filter both pass through the same -3 decibel point at the same frequency, 2500 hertz, but notice that below 2500 hertz, the gain of the Chebyshev filter is not constant. As a matter of fact, there's variation in the gain, what we call gain ripple, and it amounts to a 3 decibel variation in gain. So this is what's known as a 3 decibel Chebyshev low-pass filter. One might legitimately ask, well, point out for terminology, for the purpose of terminology here, the pass band of the Chebyshev filter, which we have this gain ripple, is known as the ripple channel. The end of the ripple channel is the same as the cutoff frequency, the -3 decibel frequency of the Butterworth filter. So if we refer to cutoff frequency or bandwidth in a Chebyshev filter and the width of the ripple channel, those terms are interchangeable. Okay. Why would we do this? Why would we accept a low-pass filter whose gain in the pass band isn't constant? Now, here's the reason. Look at the performance in the transition toward the stop band. At 5 kilohertz, the response of the Chebyshev fourth-order filter is 16 decibels below that of the Butterworth filter. The Chebyshev filter, for the same order, has a faster transition from pass band to stop band than the Butterworth filter. Or conversely, if you wanted to build a filter that had two filters that had similar transition characteristics from pass band to stop band, a Chebyshev filter would have a lower order than the Butterworth filter. So by accepting a ripple in the gain in the pass band, the Chebyshev filter gives us either faster transition to the stop band, or it gives us an equivalent transition to the stop band with a simpler, lower order filter. Okay. So let's specify the prototype that we're going to design. Let's make it a 5th order, 1 decibel Chebyshev filter. So the gain ripple in the pass band should be 1 decibel. And when the gain finally drops by 1 decibel for the last time, that will be the end of the ripple channel. And let's put the end of the ripple channel at 1 kilohertz. Let's give it a maximum gain of 0 decibels, or unity. And this is really all the specification we need to design the filter. Now, the design process with the resources in the One Human Lifetime Project requires the use of 2 separate spreadsheets. It was probably not as elegant a solution as could have been done, but it was what I did. So it is what it is. Let's take a look at the first of those two spreadsheets. The first of the two spreadsheets is this one, which has the file name Chebyshev LPF, that is low pass filter poles. And make sure that you're using a version dated March 4th, 2023 or later. It wasn't really an error, but there was an inconvenience in the way that the results for previous versions were displayed, that this is a superior, this later versions have a superior method of displaying results. Let's just say that. So make sure you're using for March 23 or later. You have two user entered pieces of data. One is the order of the filter or the number of poles. Those two terms are equivalent. In this case, it's already filled in with a fifth order filter, and the passband ripple specified in decibels, and the default was one decibel. You can put new numbers in here for different filter designs, but since the numbers that we were going to design to were already here, we'll just work with them. Now, what this gives you, we are looking for two things here. We are looking for the coefficients of the denominator of the characteristic equation of second order filter sections. This is going to be a fifth order filter, so we will have two second order sections, and we will have one first order section. And we're going to look for the coefficients of the characteristic equation of the second order sections, and we will also read the value that we need to design the first order section as well from the spreadsheet. So if you look at these two columns here, you'll see these. Well, let's move over here. Pole number 1 through 5. And you'll notice that these poles, if they are complex, that is, if they have a non-zero imaginary part, they occur in what are known as complex conjugate pairs. Two poles having the same real value, but having imaginary components that are the same magnitude, but of opposite signs. When I multiply these complex conjugate poles together to form the characteristic equation, these two poles produce these coefficients B and C for the characteristic equation. Now you notice that this pole, which is the complex conjugate of the first one, also produces the same two sets of numbers. So there's a redundancy in this spreadsheet. You notice that this set of numbers and this set are the same, this and this are the same. We don't need all 8 of these numbers, just these 4 are sufficient. So for one second order section, the coefficient B, the linear term of the characteristic equation, is 0.1789, and the constant term is 0.9883. And for the other one, the other second order section, it's 0.4684, and the C coefficient, the constant term, is 0.4293. Now notice there's one isolated, purely real pole, has no conjugate, no complex conjugate. We use this pole to design a first order section, or a first order section. So let's take note of this. We only need the magnitude. We don't need the sign. The number is 0.2895. Okay, so we take these numerical data and we go now to the second spreadsheet, which we will use for designing the two second order sections. This is the second spreadsheet. This is the one that is used to design the second order sections of this filter. This file name is Salenki Chebyshev low pass second order filter section worksheet. And it looks very similar to the worksheets that were in the Salenki filter design. And that's no accident. They did share a common origin. User entered data are in yellow, and of the four passive components in this network, you get to choose the values of three of them. The fourth one is determined once you've already chosen three. Hence, the value of R1 here is calculated in the spreadsheet. There's a formula here. Don't change this number. And we're going to choose capacitors that are in ratios that are available from standard components. So the design strategy here will be to vary resistor R4 to get our filter to match the coefficients that came, the B and C, as I called them, coefficients that we got from the Chebyshev low-pass poles worksheet. Okay, so the value for the B coefficient is entered here, value for the C coefficient is entered here, and here we enter the gain, the DC value of voltage gain of the voltage-controlled voltage source amplifier. All right, so the voltage gain is set to 1. That's what we're going to use anyway, so we don't have to do anything there. Let's change B here from its initial value to 0.1789. And let's change C to the value of 0.9883. All right. Now, the calculated value of B from the component values and the gain of the amplifier is computed here. And as you can see, it's not at all close. Let's try running the solver. And the solver has not really done us much good. The computed value of B is really not terribly close to what we want. All right, let's see if we might be able to nudge the solution in the right direction by changing the capacitor value. Let's try 5.6 farads instead of 3.3 here. And that's an improvement in the calculated value of B, but let's see if that's sufficient to allow a solution to be found. And the calculated minimum is 0.2657, still not close enough. So let's try 10 farads. Up, I typed 0. Let's try 10. There we go. And that gives us a calculated value of 0.2072. We're not very far off. Let's see if we can, that gets us sufficiently close to find a solution. No, not yet there. Okay, let's try 15 farads. And let's go to the solver. It's having a momentary outage there, looking for the solver. Okay, and it's found a solution. We've matched the coefficients for B and C. And okay, then the next step is to scale the design. This is for these components are for a filter with a ripple channel width of 1 radian per second. We want to now move the end of the ripple channel to 1 kilohertz, or 2 pi times 1,000 radians per second. 1,000 happens to be the number that was filled in the spreadsheet to begin with, so we've already done the scaling step. So now we move to choosing practical capacitor values. And C6, the initial value that was in the spreadsheet is 1 nanofarad. And that produces 0.15 microfarad for C2. And that gives us 8.35 K for R1 and 20.5 K for R4. Those seem to be reasonable values, not extremely low or extremely high. So I'd say we have a solution for the first second order section. Okay, so now let's go on to the second order, the second section of the second order section. For that, the coefficient B was 0.4684. So let me change that. 4684. And the C coefficient was 0.4293. Let's do that. Now, just for grins, I'm going to try running solver without touching the capacitor values. Maybe there will also be a solution. It would be nice if I can use the same capacitors in 2 separate sections. Let's do the solver, and we do appear to have found a solution. And it's using the same capacitors of 1 nanofarad and 0.15 microfarad. R1 is 2.30 K, and R4 is 1.71 times 10 to the 5th, or 171 K. So we now have the design of our 2 second order sections. The only thing we have left to do is to figure out how to do the first order section. And I will bring up the schematic, and I will show you on the schematic how we do that. Here is the complete 5th order filter. Here are the 2 second order sections that we designed with the help of the Chebyshev low pass second order design worksheet. And here is the first order section. Now, how I calculated these component values, you remember that there was a coefficient of the isolated pole that came from the Chebyshev low pass filter poles worksheet was 0.2895. So I took 0.2895, multiplied it by 2 pi times 1,000, and then took the reciprocal of that. So in other words, 1 over quantity 0.2895 times 2 pi times 1,000, close quantity. And that gives me the RC time constant of the resistor and capacitor in this first order section. That time constant turns out to be 549.8 microseconds. And I implemented it with a standard value capacitor of 0.022 microfarad and a resistance of 25 K. All right. So there is our complete filter design. And now let's take a look at its response. This is the frequency response of our 5th order Chebyshev low pass filter design. 0 decibels at low frequency. And we have 1 decibel ripple in the pass band. And then when the gain finally drops below 1 decibel and rolls off from there, the final time it passes through -1 decibel, the end of the ripple channel is right at 1 kilohertz. So I would say that our design is successful. All right. Now, you can design even order or odd order filters with the resources that are available here. There is just one important caveat that I should mention in designing even order filters. And let me go back to the 4th order filter response, and I'll show you what that is. This is, again, from the comparison of the 4th order Butterworth and 4th order Chebyshev low pass filters. I want you to take a look at the low frequency response of the Chebyshev filter. At low frequencies in an even order Chebyshev filter, the gain in the ripple channel is at its minimum. In an odd order filter, it's at its maximum. But again, it's at its minimum in an even order filter. So if the maximal gain in the ripple channel is going to be 0 decibels, as it is here, then the low frequency, or the DC gain, has to be, in this case, -3 decibels. That requires a little modification to the design. And let me show you what that is. Here are the schematics of that fourth order Butterworth filter and the corresponding fourth order Chebyshev filter. Here's what I wanted to show you. In order to make the gain of this circuit -3 decibels at low frequencies, it was necessary to cut the gain of one of these two stages by a factor, instead of a unity gain at low frequency, it should have a gain of the square root of 2/2. It should be a gain reduction of 3 decibels. And I accomplished that by taking R1 of 1 second order section and turning it into a voltage divider so that the voltage that would appear here is the Thevenin equivalent voltage that would appear at this point would be 0.7071, or √2/2 times the voltage here. And the parallel combination of the two resistors would equal the computed value of R1 from the design spreadsheet. Okay. All right. So let's put the wraps on it. Remember, the link to the One Human Lifetime Project resources on filters will be in the video description that accompanies this video. And if the resources are useful to you, then leave a comment. Let us know. We always appreciate feedback. And as always, we appreciate your visiting with us. Keep those cards and letters coming. And I am David Beams. It has been my privilege to present this to you. And we will see you again soon in another video from the One Human Lifetime Project. Thank you for your time and attention.